Hello and welcome to Vehicle Mechatronics Control. This video is part of the first week lecture, and the point is to show a little bit of where does the variables and equations displayed in the lecture come from, what is the origin. So a little bit of a walkthrough. So here we have the side view of a Turtlebot. So you can think that this is the right wheel and the Turtlebot is moving to that direction. We know the angular velocity of the wheel from the motor, and we also know the radius. What we don't know is the speed at this right wheel. If we think like how fast is, for example, this axis moving to the right. We can think it so that as the wheel is rotating, let's say it rotates this much, and let's call that x. Then we can draw another radius here, and let's call this angle, displacement angle, theta. And so now from geometry, we know that the distance on the perimeter on the outside of the wheel is x, that's a section, and we know that that is equal to the angle of the section times the radius of the wheel or the circle. Now if we take the derivative of both sides, we get derivative of time. So we get the derivative of displacement x or distance, and then the derivative of the angle times just the radius, because radius is constant. It's not dependent on time. It's a constant value. We could also write this in a way that's x dot and theta dot times r, the radius. Now we also know that x dot is also known as, so the derivative of space or distance is the change in distance or space is velocity, v. And we also know that the derivative of angle, so the change in the angle, is the angular rotation. So here is the formula that is shown in the lecture slides. I should also clear that this is the velocity of the ith wheel. The I refers to the wheel 1 or 2, since in our Turtlebot there are 2 different wheels. So we also need to take into account the angular velocity of the ith, the same wheel. What we have established so far is that we can calculate the velocity of the Turtlebot at wheel 1 and at wheel 2. Now in this situation, these two speeds are different, causing the Turtlebot to turn. So it's in a trajectory that looks roughly like this. It is turning around the center of rotation, which is defined by the difference between these two speeds, as you can see based on this line. So what we want to know is more than just the speeds at wheels 1 and 2. We would like to know the speed that the Turtlebot is moving forward and what is the turning angle, the current turning angle over here. So now we want to know this theta and and the average speed of the tool wheels. So this velocity here. So the velocity, as I already sort of spoiled out, is the average of these two wheel speeds. Sorry, the average speed at these two wheels, which is r, is the same for both. That's why it can be outside these brackets. And so here we have the linear velocity of the turtlebot. How fast is it moving forward? Now comes a little bit more tricky part, is how do we calculate this angle? Well, let's take a different color for this. Make this a little bit bigger. So I will draw a triangle over here, like so. And I won't just draw it for fun, it actually makes sense, believe it or not. So here we have the same theta as we had here. And now this distance between the two wheels, let's denote it L. It's the wheelbase of the turtlebot. It's something that we know. Again, similar to the radius of a wheel, it is a constant value. And then we have this part over here, which is the difference between if you think of them as vectors, the v2 and v1, that's the difference over here. This is v2 minus v1. Okay, so then we want to know this angle over here, or actually the angular rate of rotation. So we will denote it like this. We have theta dot equals minus v2 minus v1. So we have this term in brackets divided by L. Now why we have this minus over here is that the default positive direction of this angle is counterclockwise, which is, now that we're moving clockwise, we need to add a minus sign over here. So now we plug in the same way as we had here. We can have minus. We can actually put this minus into work. So as we put that minus inside, these two switch places. So we get R. Again, we can have it outside, and then it's omega 1 minus omega 2 divided by the wheel space length, L. So now we know the angular rate of rotation speed and the linear speed of the turtlebot. The linear velocity v can be split into components, since there's a change in x, so x dot, and then a change in y, y dot. So we can write these equations as follows. X dot is the velocity times the cosine of theta. Then we have y dot, which is the linear velocity, and the sine of theta. Then we will rewrite theta dot over here for a reason that you will soon notice. Omega 1 minus omega 2 divided by the wheel space. So these equations are in continuous time space. So I'll just write continuous. And let's take that line away. So I'll explain a little bit the difference between continuous and then discrete time spaces is that in reality, continuous equations are quite difficult to solve when you're, let's say that there is, I'll give you an example. There is a path that looks like this. This is now continuous line. It's in the steps in between two dots. You could think that it's created from little dots, and the distance between the dots is infinitely small. That's why it looks like a line. But that means that it's infinitely hard to compute because the steps between each of those two dots is very, very small. So instead, what we can do is we can approximate this line with, for example, splitting it into these pieces. So now it's discretized. So it's calculated at these steps. So now we can actually compute it. We have a finite number of states that we need to calculate. So then the approximation is the line that has these straight line segments from each dot to another. So make it clear, this should be straight and straight. Oh, there's actually a tool for that. Let's use that one. So there's a straight line from this, there, there, there. So as you can see, we lose some of the behavior of the continuous line. It becomes more sort of jagged. It's rigid. It's these straight lines instead of a nice curve. But we have a possibility to actually calculate these. So I'm gonna call this first spot over here gonna be called xk, and the next one is xk plus 1, so what plus 1 time step, then xk plus 2, and so on until xk plus n, as many steps as you have. Okay, now we can go back and think about these formulas over here. Right? Let's change the color and make this pen a little bit bigger. So now we want to have a formula to calculate each time step, or the x coordinate in each of these time steps. So no longer we have the x dot as change. The change will be shown as follows. It will be shown as xk plus 1. So we will straight calculate the next step by taking into account where we just were in the next step, in the last step. So xk plus, then we will have here on top the radius of a wheel, then the angular speed of wheel 1 at k at the previous time step, then wheel 2 and again at k, so in the previous one, and this is divided by 2 just as previously, and again since it's the x coordinate, we will multiply this by cosine theta, and now this whole thing, this part, is calculated by delta t, so the difference in time. So what is this now? It's the time in between these steps. So now we had, let's take this nice tool again. We had, oh, excuse me. Imagine that these are straight lines. So the delta t is the constant, the time difference in between these steps should be the same. Obviously, I didn't manage to draw it in that way, but imagine that it's so. So this is the time interval of this discretization. So that is delta t over here. So to recap, we want to calculate the next step. So xk plus 1. And we use the current location of x, so xk, as a starting point. And then we utilize this continuous equation, and we just multiply it with the delta t, so the time interval between the two spots. It could be like 2 seconds or 1 second or 1 millisecond. It's sort of the weight of how much does this equation add to the original coordinate. So if it's a very small time interval, then this has smaller weight at that point, but then there will be much more steps to take. So I'm not going to write down well, I could recap on the y coordinate, why not? So yk plus 1. So the next step, we take the current yk position, we have the radius of the wheel, and then the angular speed of wheel 1 at this current time step that we are right now. Then we take the average of these two wheels times the sine of theta to take the y component, and then this whole thing is multiplied by delta t. Now for the angle, it is very similar. So we have in the next time step, what is the angle? So the heading of the vehicle. So the output of this is that we always get, as time goes forward, we get the x and y coordinate, so the location of the robot, and the heading. Where is it headed to? So here the heading is changing to the right in each time step. So here we have theta k, so the current heading. And now we can take a look of this formula over here. So again, radius of the wheel and the current angular speed. Okay, and then it's minus. It's important to remember that we have a minus here. Oh, I noticed there's a problem. This should be a 2. So here we have 2. Again at the step k. And now again, remember that this is not divided by 2, this is divided by the wheel space L. Again, we have brackets, but that's it. This is just then multiplied with delta t. I know that there's quite a lot to take in all of this, but I hope this clears out some of the confusion you might have from the lecture slides.